Hey everyone, Internet most confused book reader here. Today I want to talk about The Origin of Time by Thomas Hertog. I mentioned this book in my review of This Ordinary Stardust by Alan Townsend. I read that book at first thinking it's related to astronomy, which is a field I'm interested to learn more about. But that book is not related at all to astronomy, since that book is more about human connection and the tragic loss that the author experienced and how he dealt with his grief using his lifetime of studying his field of science. On The Origin of Time, on the other hand, is written by Stephen Hawking, longtime collaborator, about their deep dive into quantum theory of the cosmos. So it should be closer to astronomy compared to This Ordinary Stardust. The book starts by taking us back to where the author and Stephen Hawking did their job during his last moment, Cambridge Department of Applied Mathematics and Theoretical Physics in June 1998. Stephen invited the author to his office after hearing about his performance in class and started a conversation regarding Andreas Lines' theory on inflation that becomes the new foundation of the multiverse theory. Stephen, who at that time has already started talking using the equalizer that Intel gave him, disagreed with Andreas' multiverse because he disagreed with anthropic principles where the life in the universe is inevitable, which means he has changed his mind ever since the release of A Brief History of Time. Inside of Stephen's office is many of his students' works. Brainwich, A Quantum Theory, Raymond Laflamme and Quantum Cosmology, Feithauker's Space-Time Wormholes and the Constant of Nature. There's even the dissertation of Gary Gisborne's Gravitational Radiation and Gravitational Collapse, who at one point in his life tried to construct their own gravitational wave detector to find the origin of gravitational wave with Stephen, which will only be achieved 40 years later with the construction of the Laser Interferometer Gravitational Wave Observatory. It has been a habit of him to work with different students each year to pursue his study of cosmology, and this is the reason he called the author. This year, he and the author will try to work on a quantum theory of the Big Bang so that they can finally sort out the multiverse. A theory that when solved should be able to finally unite Einstein's gravitational theory and quantum theory. The work turns out to take more than 20 years, even after the death of Stephen Hawking on March 14, 2018. And before his death in 2012, he wrote the grand design, which is what he had partially found out on the Big Bang theory and the challenges that will need to be solved. Later on, he told the author that he had to start another book, and this is the book that he meant, Stephen Hawking's Final Legacy. Ever since 1927, Belgian priest astronomer Georges Lemaitre already predicted that space is expanding, but it was not until 1990 where telescope technology was advanced enough that we get to see the speed of how it expands. In May 29, the European Space Agency launched Planck satellite and tried to scan the night sky by using the remnant heat of the universe expansion, named as Cosmic Microwave Background Radiation or CMB radiation, resulting in a map that it produced in 2013, showing almost universal level of heat in the universe about 380,000 years after the Big Bang. This small dots of much colder area eventually turns into the galaxy as we know it. While we cannot see further than that, since traces of it cannot be detected by reading their CMB radiation, we can know at least that the very fast expansion of the universe at one point slowed down before it got faster again. This slowing down is what makes matter possible to exist. It's as important as life being in 3D form because at one-dimensional or more, and it'll become too chaotic, and 2D makes some life basic function impossible. This along with carbon, which is what made up life forms, among other things, which in turn is created from the nuclear fusion of stars, and how small the amount of dark energy seems to indicate that the universe feels like it is tailor-made to support some form of life. And this is what physicists call the laws of nature, and ever since Aristotle, who is considered the father of science, the design of the world is seen as evidence that there is a purpose to the working of nature. But because of how influential Aristotle is, a lot of his work was accepted without much question. Remember that the Greeks also used to make and popularize humorism, which is why when germ theory was brought up, there's a lot of fight back on the idea that germs is what cause sickness instead of humor. The first to start a journey of curiosity on how nature works is Anaximander, the teacher of Pythagoras, and the one who is considered to be the father of cosmology. He is the first to suggest that Earth is a planet in a celestial body, and he is the one that started trying to find the laws that governs nature. A quest that is later expanded further by his pupil Pythagoras through the use of numbers and mathematics, which is expanded further by Pythagoras' pupil Plato, and so on until Galileo, and then Isaac Newton, who wrote Principia, a book that consolidated the mathematical approach to natural philosophy. And with Isaac Newton during the plague in 1665 during lockdown, while a lot of people are protesting from having to wear masks, Newton wrote Philosophiae Naturalis Principia Mathematica, which contains the three laws of motion and the laws of universal gravitation. The latter will eventually be used to help discover the location of Neptune by reading the wobble in Uranus' orbit by Leverrier. Ever since then, theoretical physics has been using math as a foundation to predict things before it happens, and it has proven to be successful time and time again. And it seems that the design of our world that is really very naturally designed to have life feels like it had a designer. That is, at least until Charles Darwin shows that things can evolve naturally to adapt itself to nature. Darwin theory shows that there is unpredictability in life that theoretical physics at that time cannot show, like how nature can branch into many forms, and we cannot predict which one will eventually survive. Because of this, Darwin theory enhanced our understanding of the living world instead of twist it. After Darwin, physicists approach to multiverse theory and string theory itself changed. Stephen Hawking work itself has been trying to bridge the gap between biology and physics, between the unpredictable and the predictable. They were trying to figure out the rule that governs the difference between the meta laws of the multiverse and the local law of our universe. That's how the proposal of the anthropic principle comes in. In 1973, Brandon Carter, a fellow student of Cambridge as Stephen Hawking, suggested a theory that the evolutionary selection of living organisms is not just in our evolutionary tree, but happens across the multiverse where only a few universes manage to contain life. The story had its merit, and some physicists like Leonard Susskind, whose theoretical minimum book I've read, at one point has tried to bridge the objective meta-laws with the objective anthropic principle to create a new paradigm for fundamental physics in his book The Cosmic Landscape. Stephen Hawking himself, as mentioned, has tried his hand on anthropic principle, but because with anthropic principle it means that every theory can be right and wrong at the same time because of how his version of multiverse is built, he had since distanced himself from it. Even Darwin in his theory rejected anthropic principle. There is no mention of extraterrestrial organism or superior species that becomes the one true winner of evolution in Darwinism. It's just a natural progression of things that might one day be replaced naturally by another evolutionary trait, which is very different from Carter's anthropic multiverse. So we face a paradox in this current understanding of multiverse. On one hand, all the best theory on how our universe happens support the existence of multiverse, but the existence of multiverse destroys our predictability of the multiverse itself. And this is not the first paradox that Stephen had to face. Back in 1977, he made a theory that in quantum theory, it means that black hole doesn't just suck up and hides all the information it devours forever, because black hole also radiates its own energy, which will later be known as the Hawking radiation. So that means it will eventually run out of energy and disappear along with all the information it contains. But in quantum theory, physical process can only transfer information, not entirely obliterate it, which creates a paradox. And this paradox is quite important because it's a paradox between the two pillars of physics, general relativity and quantum theory. And asking these questions through theoretical physics experiments is how Stephen got three of his landmark discoveries. The first is the Big Bang singularity theorem, the second is Hawking radiation in black holes, the third is his proposal of the origin of the universe, and his fourth and last thought experiment that he left behind is a step beyond that, the origin of time itself, a day without yesterday. And in order to tell this theory, the author first go back to before Einstein's theory of relativity, right after Newton's law of gravity and motion and James Maxwell's theory of electricity, magnetism, and light, we had the Industrial Revolution. Because of how much of a jump it was in our understanding of physics, a lot of scientists at that time thought that physics will be soon wrapped up and finished. But William Thomson and Lord Kelvin found two major discoveries in 1900s. One is the movement of light in the ether, and the second is how hot objects emit radiation. This discovery will eventually become the revolutionary relativity and quantum theory, which goes on in two very different directions. The first one, the light in the ether, is a problem because it shows the speed of light is always constant no matter how you observe it, which doesn't really match with everyday experience because if you're watching a light source from inside a moving train or outside it, you view the speed it comes and goes differently. And speed is a measure of distance between travel divided by the duration of the journey. And our understanding at that time is that light is carried through this unknown space called ether, which should make everyone observe light at a different speed depending on where they are. This is when Einstein theorized that speed itself is related to space and time, and that we are moving at the maximum speed possible through space, breaking apart from the previous Newtonian understanding that space is fixed and separate from time. This also means that Einstein had to change our understanding of Newton's gravity, since it is incompatible with general relativity because it added space in its calculation. Gravity is not just a pulling force, but a bending of space and time, creating what looks like a geometry in its depiction which not only put us to the ground but also light and time. And this is why I love learning about cosmology. It's one of the best ways to show the scientific approach on how it builds one another and show acceptance and adaptability to mistakes. So being right is not just for the sake of proving someone else is wrong, but for a better understanding of the world. Using Einstein's new calculation, we managed to fix the projection of Mercury orbit, which has never been correct using Newton's calculation. General relativity also helped fund the existence of black hole. Karl Schwarzschild made the first solution about a strongly curved geometry outside of an extremely dense mass, which will later become the work of Roger Penrose that showed that every sufficiently massive star will collapse into a black hole. On a rare occasion, two black holes might even collide and combine, creating gravitational waves that are larger than any stars combined. These waves were theorized quite early in 1965, but was only proven by 2015 when we built the LIGO. Einstein then met with Lemaitre that has been mentioned at the start of the book, who he had a lot of back and forth disagreement about the expanding of the universe and the constant energy it left behind, both of which is proven to be true many decades later with the LIGO. And during his research, the priest made this diagram that showed the expansion of the universe, which contained the symbol for t equals 0 that indicates the start of the universe, the start of time, where the universe starts because of a bang somewhere. At first, the theory was rejected even by Einstein because at that time, physicists think that they're close to solving the universe, so a theory that the universe starts with an unknown is an unpopular opinion. And it is here that he wrote The Beginning of the World from the point of view of quantum theory, where he proposed a connection between general relativity and quantum theory. It is often called as the Big Bang theory. While most physicists remain skeptic to the Big Bang theory, there are a few that works with quantum theory that made their own work based on it. Paul Dirac, who later on will make the equation that unites general relativity and quantum theory and predicted antimatter, and George Gamow, a nuclear physicist that predicted that the Big Bang will leave a ton of radiation, which is proven to be true later on when Arno Belsius and Robert Wilson found a hiss from the satellite they were testing that they cannot get rid of no matter where they pointed their satellite. It's because it is catching fine relic radiation from the Big Bang. And seeing this long-lasting effect on the universe expansion finally changed public opinion on the Big Bang theory. And once again, just like we changed how we view the world from Newton's perspective to Einstein's perspective, we change our perspective from Einstein to Lemaitre. Early Stephen Hawking himself worked based on Einstein's works, but he'll start his later works using Lemaitre's works. It's not easy work as you might have guessed. All current calculations don't hold once we get close to the singularity near the Big Bang, and there are some things from the observable universe, like how almost universally hot the CMB are for a universe that is still expanding. To do that, he had to be able to fully marry relativity to quantum theory, which is still separate at that time. So let's talk first about quantum theory. If Maxwell electromagnetism enabled the revolution industry, then quantum theory makes our current technology possible. And we're not even close to how small technology can go, because theoretically at least, we can get a quantum computer that enables more powerful computing prowess than the best we currently have. Unfortunately, at this point, the book once again had to go back to the past because of how different general relativity and quantum theory is. A study of physics on very small things, quantum theory starts in 1900s when Max Planck suggests that anything when heated emits small amount of radiation he calls quanta. He wanted to help explain how much light each color hot bodies radiates. In Maxwell's classical theory, light is made of electromagnetic waves of different frequencies, corresponding to different colors. But Maxwell's theory also says that energy radiated by a hot body are shared equally among waves of all frequencies. And also in Maxwell's theory, all electromagnetic waves have high frequencies, so the radiation sum of all frequencies becomes infinite, which is just not possible. This is called ultraviolet catastrophe because the highest frequency visible light are violet. So Planck made a proposition that each frequencies can only emit a certain amount of quanta, and the greater the energy emitted, the greater its frequency, which avoid the catastrophes to happen. Then in 1905, Einstein showed that electrons moving around in metal can only absorb certain amount of quanta, which he described as tiny particles of photons. And this means that light are both wave and particle at the same time, which is still mind-blowing no matter how many times I read about it. But after that, every physicist was stumped for a while. They even had a meeting in Brussels during 1911 with no result. It was not until 1920 when Werner Heisenberg came up with quantum uncertainties, where you cannot know the position and velocity of a particle at the same time, either one or the other. And this uncertainty is absolute. There is no changing it no matter how hard you monitor them. So there is a limit to information in quantum physics, where studying it will be not only about what you know, but about what you cannot know. It's about probabilities instead of determinism. You can see this even more clearly in the famous double slit experiment. I'm sure you heard of it if you've gone this far into the video, which thank you by the way. But if you haven't heard it, The double-slit experiment is where they prepare an electron gun that shoots every few seconds, that goes through a double slit and into a screen. If it's a particle, it should result in two spots filled with traces of electron, but if we run the experiments long enough, somehow the traces show what is only possible if light is a wave. The next breakthrough is with Richard Feynman, where he is trying to determine how photon path goes. In classical theory, A goes to B in a single path, but in quantum, you have to calculate the probabilities of every single path. He wrote an equation for the probability of which path the photon might take based on everything in each path, length, obstacle, etc. And he even wrote about them, which helps explain further the difference between relativity and quantum theory. That just because it is different, it doesn't necessarily contradict it, because the probabilities of the micro in quantum is what caused the determinism in the macro of classical physics. He called this sum over history. A principle that Stephen Hawking eventually tried to use not just in light but in gravity. He took the uncertainty of particles to a black hole and replaced the single point of origin in singularity with the fuzziness of quantum where time dissolves into space, changing our view on the Big Bang theory by making the origin of the universe lost in quantum uncertainties the closer we get to a time before time exists. That's when they got to the idea to calculate its space with imaginary time, just like when we theorized that the existence of atoms before we can see it. And that was just the start of Hawking's no-boundary hypothesis that is still based mostly on Einstein's work. It is not until his next step forward into his no-boundary hypothesis that the author came in. The second string theory revolution seems unstoppable, and the advancement to telescope technology means that we can finally observe what has been theorized so far, making cosmology change from mere speculation into a quantitative research field during this time. And one of the other theories that at the time is popular besides Stephen's theory is the cosmic inflation theory, which suggests that at the start of the universe, the expansion is much faster than any of the rest of the billion years of its history. It uses a scalar field that is called inflation field that imagines anti-gravity that is stronger than its gravity, which accelerates its expansion. It explains the heat and the radiation it left behind, and it even explains the spot of cooldown the CMB map, but it cannot explain the primordial gravitational wave which should be there if cosmic inflation theory is correct. Stephen even helped theorize ways to find it because its existence will not only proves the cosmic inflation, but also the Hawking radiation. He put his no-boundary proposal into the cosmic inflation theory, but they got nothing but disappointment so far from it because it cannot create the galaxies as we know it now with these calculations. Then comes a rival vision for them by Andrei Linde and Alexander Valenkin. They suggested that inflation does not just happen at the start of the universe expansion, but throughout the whole expansion. An eternal inflation which causes an infinite multiverse where every jitters during an inflation causes another universe and so on and so forth. And this gained more traction than Stephen's no-boundary theory that even string theorists are getting their hand on trying to solve the universe using the multiverse. String theory is a theory proposed in mid-1918 where the matter once dissected into the small scale had tiny vibrating strands of energy. And the difference in matter, for example, between atom and neutron is how the string vibrates. String theory can help unite relativity and quantum theory, but it only mathematically works in a 6-dimensional world. And this 6-dimensional bubble is so small that we cannot see it in our 3-dimensional life. And playing around with the shape of this bubble theoretically gave us different kind of physics and thus different kind of universes. But the more Stephen Hawking learned about our universe, the more he grew to see both the anthropic principle that life will always exist and the multiverse as fundamentally weak because it adds too much assumption in its basis. Atom, Darwinism, and even quantum theory is at least still based on our observation. But both the anthropic principle and the multiverse version of this had to insert too much assumption that we might never be able to observe at all to consider it as usable. So Stephen and the authors started working on something new. Stephen Hawking works and most cosmologists is using the Copernicus way of looking at the world with a God-eye vantage point of view as if they are an outsider observer. But so far he has led them to this dead end of multiverse that only got more popular after a few Marvel and DC movies. So in this newer time, they'll try to use what Stephen called a warm eye point of view, looking at the cosmos from an insider perspective this time, where he'll even have to throw out a lot of his previous work that is not yet based on a quantum theory, but from classical theories. For example, Huey Everett III approach to Schrodinger's cat, where he not only observed the cat where it is dead and alive at the same time, but this time, he also looked at Schrodinger's cat along with the observer, involving the quantum uncertainties and everything else too to see whether they will look or not look into the cat, causing a multiverse which added a lot of subjective perspective into the theory, because in quantum, the act of observation itself changes things. That is why Stephen Hawking proposed that instead of using the usual bottom-up approach of looking into the cosmos, Instead, they use a top-down approach, identifying as much law-like pattern in your data as you can and use them to construct histories of the universe, ending up like the one you observe. So instead of the bottom-up approach of making everything into absolutes, top-down cosmology prioritizes the historical nature of everything, tying the tangible universe and the observers on a quantum level. And with this new way of seeing cosmology, Stephen finally solved the problem with his no-boundary universe. He can see now all the galaxies that we've seen with the new approach. It is such a good book to learn more about cosmology, even if you have no background on the field like me. It's not the most well written, with parts really feels repetitive and other parts around the end doesn't have much to them, but it contains most of what you need without all the detail where you'll need to have much more expertise into the field to understand. If you just wanted a clearer understanding of the basic about the history of physics and what we can look forward to, I at least never found a better book that helps like this one. The book in a way is also a very moving farewell to the figure that is Stephen Hawking and how much he meant to the cosmology community. It's not just because he's famous, even if that factors a little bit, seeing at how much dumbness is prevalent in the internet nowadays without a figure like him, but also because he, as not just a cosmologist, but also as a person, is awe-inspiring in a way. Even to the end of his life, he's still full of life, even going through a no-gravity experience, and still going to speech despite his difficulty of talking even with his machine around the end of his life. And even the last few interactions he had with the author, when he had to have another machine attached to him just to help him breathe, he still tried to focus on solving the mystery of the universe instead of spending his day frustrated on the things that he can no longer do. We still don't know if anything new will come out of the top-down approach on viewing the universe, but I think it's such a waste to just throw it out the window without even trying it, saying how much in history ideas that was abandoned so early are often helpful in helping resolve physics conundrum. I give this a 4.25. What do you think? Let me know if you missed anything, so leave your thoughts in the comment below and subscribe to the channel. That's about it. See ya.